Dear student, in continuation to my lecture series of normalization, in last lecture, I discussed with you the how to check the lossless decomposition, right? And in this lecture, I'm going to discuss with you the dependency preserving algorithm. So in last lecture, when we just discussed the lossless decomposition, then we solve all these numericals in lossless decomposition. So there I told you कि in normalization, that when you do the normalization, then the two things, the first is the lossless decomposition, lossless decomposition, and second one is the dependency preserving. These are the important dependency preserving, right? This lossless decomposition is mandatory. That means when you decompose a relation, then this lossless decomposition is mandatory. It must be there. And this dependency preserving is not necessarily always it is dependency preserving, not mandatory. It is not necessary in all the cases the dependency preserving is there. So what I'm doing over here, I'm just discussing over here the one analogy with you, right? Suppose in a class there are number of students, right? And suppose the name of the student is A, B, C, D, E, like this, right? All the students belong to one class. And suppose this is A placed in Google and B placed in FB and this placed in Microsoft and D again placed in Google and E placed in Oracle, right? So when they just pass from the university, at that moment of time, there is a relationship. And I just talk about the relationship over here, then the in in college time, A belong to B is in touch with B, C, D, or E. Here, don't think about this is the functional dependency. I'm just explaining the analogy over here, right? Okay, why lossless is important? Why dependency preserving is important? Why lossless is mandatory? Why dependency preserving is not mandatory, right? See, if I just talk about the friendship in college time, then A belong to B, C, D, E, right? But what happened after 15 years? When just 15 years passed out, then what happened? After 15 years, is the same relationship maintained over there? No. It is not necessary the same relationship maintained over there. At that moment of time, maybe the A belong to BC, and C belong to D, C belong to D, and E is not associated, not linked with anyone. It is possible. So if I talk about at that time relationship, so at that time the relationship is A belong to B, C, and C belong to D. This. So this relationship is there. This relationship is there, but A is not belong to E. A is not belong to E. A is not in touch with E. Right? So what is necessary? The important thing is everybody should there means yes, A, B, C, D, E should be there. Maybe E is somewhere in the universe or in company, but not in touch with all other friends. So the talk about the relationship, then this relationship A to E is not maintained over here, right? So what is necessary? It doesn't matter ki relationship is there after 15 years or not, but all must be there. This is the important thing. All must be there. Similar over here, if we talk about the relation, relation R is there, and in relation R, A, B, C, D, E, F attributes over there, and we decompose this A, B, C, D attribute like A, B, C, A, B, A, B, C, and C, D, E, and E, F, like this one. If I just decompose it, then in decomposition, all attributes should be there. So A, B, C, D, E, F, all attributes should be there. But if I just decompose this in these two tables, then what happened? There is a loss of one attribute over there. There is loss of one attribute over there, right? So this thing you can relate with the lossless decomposition. That means there are two aspects. The one aspect is there is no loss of attributes, and the another aspect is there is no loss of functional dependency. So the loss of attribute we are talking about in terms of, like you can say in a lossless decomposition, and about functional dependency in dependency preserving, right? So here what I'm doing, I'm just discussing with you this dependency preserving algorithm, right? See what happens. If a relation R, A, B, C, D is given to you and a set of functional dependency, A determine B, B determine C, A determine B, B determine C, C determine D, and D determine A is given to you. And the decomposition R1AB, R2BC, and R3CD is lossless and dependency preserving, right? Is lossless and dependency preserving. So first we should check, is this lossless? Because if it is not lossless, then no need to check the dependency preserving. So for checking the lossless, what you can do over here, just write R1. You can use the method that we discussed in previous lecture, is the tabular method. And here I am discussing the another method, another shortcut you can say, right? So you can also solve it by the help of the tabular method that we discussed in the last lecture. And here I am discussing this method. See, for lossless, this is also another method. What you can do, there are three relation R1, R2, R3. In these three relation, what is the common attribute from R1 or R2? In R1 or R2, we will see, then B is the common attribute. Similar over here, what is the common attribute over here? C is the common attribute over there. If this B is candidate key in any one of them relation in R1 or R2, if this B is the candidate key of any one relation R1 or R2, and if this C is any one relation from R2 or R3 candidate key, if this C is candidate key in any one of R2 or R3, if both condition, if B is the candidate key in this and this, in this or this, or if C is the candidate key in this or this, if any one of them, if C is the candidate key, or similar over here, B is the candidate key, then we can say, yes, this is the lossless decomposition, right? So if you find the closure of B over here, then what happened from this set of FD? This set of FD, the closure of B is B, B, C. So if we talk about in this, yes, in this B is the candidate key. So yes, okay. Now check over here, C, yes, in this C is the candidate key. C determine D is the C is the candidate key. So we can say, yes, this is the lossless decomposition, right? Now I'm going to discuss with you dependency preserving algorithm, right? So in checking the dependency preserving algorithm, what is the method? The method is like this. See, what you have to do, just write the R1 like AB, write the R2 like BC, write the R3 like CD, right? Now what you have to do, you have to find the closure of all the attributes and all the possible attributes, like A, B over here. So write the closure of A, write the closure of B. What is the closure of A? The closure of A from the this set of functional dependency is A, B, C, D, all, right? And the closure of B is B, C, D, A, all. Similar over here, if we talk about the closure of B, the closure of B, the closure of B is B, C, B, C, D, A. So what I'm doing over here, I'm just finding the closure of B in respect to all relation. But if you talk about just in respect to in this relation, then no need to write D and A. If you write over here, then there's no problem, but no need to write D over here because we're talking about in terms of BC, right? So when you find the closure of C, then the is C, D, A, and B like this. If you talk about the closure of C, so C is C, D, A, B, and the closure of D again A, B, C, D. The whole the closure of this one, right? Now what happened? Now what you have to do? You have to find out the functional dependency in this relation. How you find out the functional dependency? See, A determine A, no need to write it. A determine B, yes, B is there. So write here A determine B. A arrow C, no need to write over here because C is not there. A determine D, no need to write it here because D is not there. Now for this one, B determine C. C is not there, no need to write it. D is not there, no need to write it. A is there, yes. So B determine A, yes. So 2FD you got from here. Now similar here, B determine this. B determine B, no need to write it. B determine C, okay. B determine D, no need to write. B determine A, no need to write because D or A is not there. Similar over here, C. C determine, yes, B is there, B is there. Similar over here, C determine D and D determines C, right? Now what happened? As we discussed in previous analogy, what happened? This is the relationship, when all the student placed in different companies after 15 years. Now, if after 15 years, if the union of all these, is the whole FD that is given previously, then you can say, yes, this is lossless decomposition. Like for example, check A determine B. Yes, A determine B is there. Okay. B determines C. B determines C is there. C determine D. C determine D is there. D determine A. D determine A. So D determine A can comes over here. D determine C and C determine B and B determine A. C, D determine C, C determine B, and B determine A. So from here you can write D determine A, right? So the last FD is also there. So all the FD which is given previously, all the relationship which exists in beginning, that all the relationship is maintained over here also, right? So you can relate it from that analogy also. So here the union of all these FD is the previous one. So here you can write yes, yes, it is dependency preserving, right? So yes, it is lossless decomposition, and yes, it is dependency preserving, right? So I hope all of you understand